Welcome to an exploration of Paul Dirac's mind, the architect of modern physics. Renowned as quantum theory's most enigmatic genius, Dirac's introverted demeanor concealed a remarkable intellect. This slide highlights his substantial contributions to science, particularly through the Dirac equation. Formulated in 1928, this elegant equation successfully unified quantum mechanics with Albert Einstein's special theory of relativity. It describes the behavior of spin 1/2 particles, such as electrons, and famously predicted the existence of antimatter. The Dirac equation stands as a testament to the profound insights and beautiful mathematics of a man who fundamentally transformed our understanding of the universe. Paul Dirac was a man of striking contradictions, embodying both a towering intellect and an eccentric personality. On one hand, he was known as the theoretical titan. He held the prestigious Lucasian Chair of Mathematics at Cambridge for 37 years, won the Nobel Prize in Physics at the young age of 31, and was a key figure in the development of quantum electrodynamics, QED, and quantum field theory. On the other hand, he earned the nickname, the strangest man. Niels Bohr described him as a complete logical genius but also the strangest person he had ever met. Renowned for his extreme taciturnity, rigid behavior, and complete lack of social pretense, Dirac lived by a simple creed: he valued mathematical beauty above all other human endeavors. To understand Paul Dirac, we must trace his extreme introversion and reliance on internal logic back to his formative years in Bristol. First, let's consider the dining room crucible. His father strictly enforced the rule that Paul could only speak grammatically correct French at dinner. To avoid making mistakes, Paul chose to remain completely silent, which ignited a lifelong aversion to unnecessary speech. Next, we have the engineering detour. Paul graduated with a degree in electrical engineering from the University of Bristol in 1921. During this time, he learned to appreciate approximations and the pragmatic application of mathematics to real-world problems. Finally, there is the geometric mind. With the opportunity for free tuition, he decided to study mathematics and fell in love with projective geometry. This discipline allowed him to visualize complex relativistic spaces, setting the stage for his groundbreaking contributions to quantum physics. By the 1920s, physics faced a significant theoretical gap, which categorized the universe into regimes based on size and speed. For large and slow-moving objects, Newton's classical mechanics served as the dominant framework. When objects became large and moved at incredibly high speeds, Einstein's special relativity took over, famously expressed by the equation E equals mc squared. In the realm of slow-moving, microscopic particles, Schrödinger and Heisenberg established the foundations of quantum mechanics. However, a prominent blind spot remained at the intersection of the very small and the very fast. This missing link, highlighted in purple, was relativistic quantum mechanics, the unresolved physics concerning high-speed electrons. Bridging this profound divide would require a mind capable of rewriting the fundamental rules of reality. In 1926, Paul Dirac resolved a significant debate in physics by unifying two competing theories into a single mathematical framework known as transformation theory. One side of the debate was represented by Heisenberg's matrix mechanics, which described particles in terms of discrete states and quantum jumps. The other side was Schrödinger's wave mechanics, which viewed particles as continuous waves. While reviewing Heisenberg's proofs, Dirac discovered that non-commuting variables, where the product of two variables p times q does not equal q times p, closely resembled classical Poisson brackets. With this insight, he demonstrated that matrix mechanics and wave mechanics are completely equivalent. They are simply different mathematical representations of the same underlying quantum state vectors. This discovery harmonized the foundations of quantum physics. In 1928, Paul Dirac introduced his groundbreaking work, the Dirac Equation, as displayed on this slide. To reconcile the principles of relativity with quantum probability, Dirac employed first-order derivatives, ensuring a symmetrical balance between space and time. He expanded Pauli's spin matrices into 4x4 matrices, denoted as alpha and beta, to accommodate the four-dimensional nature of spacetime. Importantly, the spinor, psi, emerged as a four-component wave function that inherently governed the electron's spin and magnetic moment on fundamental grounds. Finally, Einstein's rest mass energy was elegantly incorporated, firmly integrating relativity into the quantum framework. This slide illustrates Paul Dirac's boldest prediction, the existence of antimatter and the concept of the Dirac sea. This theory revealed the mathematical necessity of the anti-electron through three distinct steps. Step 1. The vacuum. The universe is envisioned as an infinite sea, filled with negative energy electrons, which are kept from collapsing further by the Pauli exclusion principle. Step 2. Excitation. A high-energy gamma-ray photon strikes one of these negative energy electrons, boosting it past the zero-energy threshold into a normal, positive energy state. Step 3. The hole. The escaped electron leaves behind an empty hole in the sea. This absence of negative charge behaves like a particle with a positive charge and positive mass, the anti-electron. This timeline highlights the significant experimental validation of Dirac's work, illustrating how his pure mathematics compelled experimental physics to catch up. In 1928, Dirac's equation introduced the concept of negative energy states. Initially, he was hesitant to predict particles that had not yet been observed, instead explaining these states as protons. However, by 1931, convinced by his own mathematical findings, he published a paper officially predicting the existence of the anti-electron, a counterpart to the electron. Validation came quickly in 1932, when Carl Anderson discovered the positron in cosmic ray cloud chamber tracks at Caltech. This remarkable discovery culminated in 1933 when, at just 31 years old, Dirac was awarded the Nobel Prize alongside Schrödinger, an honor that the publicity-shy genius initially contemplated declining. This slide delves into Paul Dirac's defining philosophy, the mathematical aesthetic. It highlights his famous quote, "It is more important to have beauty in one's equations than to have them fit experiment." To achieve this beauty, Dirac developed what is known as the Dirac toolkit, a collection of significant contributions that reshaped the language of quantum mechanics. 1. Bra-ket notation. He created this elegant and universal syntax for calculating quantum states. 2. Dirac delta function. This concept, known for its mathematical elegance, was developed to represent idealized point masses and charges. 3. Fermions and bosons. Dirac permanently organized the field of physics by coining the terms for the two fundamental classes of particles in the universe. This slide outlines Dirac's foundational role in the development of quantum electrodynamics, QED. Early quantum mechanics faced a significant challenge. It could not adequately explain how a photon could be physically created from nothing. Dirac's solution emerged in 1927 through the concept of second quantization, which describes a three-part cycle. 1. The field operator. Dirac conceptualized the electromagnetic field as a quantum harmonic oscillator acting upon the vacuum state. 2. Electron transition. An electron transitions to a lower atomic energy level. 3. Photon creation. A photon is mathematically created, or annihilated, as energy is exchanged. The historic outcome was the birth of QED, which remains the most rigorously tested and accurate theory in the history of science. This slide examines the legacy of the taciturn genius by sharing four legendary stories that illustrate Paul Dirac's extreme, literal-minded nature. 1. The comment. When a student interrupted a lecture to say they didn't understand an equation, Dirac remained silent. After a moment, he explained, that was not a question, it was a comment. 2. The sheep. While traveling on a train, a companion pointed out a flock of recently sheared sheep. Dirac observed them and precisely replied, sheared on this side. 3. The unit. His Cambridge colleagues jokingly defined a new conversational unit of measurement. 1. Dirac equals 1 word per hour. 4. The redundancy. When advised to label a draft, not to publish in any form, Dirac stared for 15 minutes before asking, don't you think the phrase, in any form, is redundant? Every great force has an equal and opposite reaction, and for Paul Dirac, that force was his wife, Mansi Wigner. This slide examines the antiparticle, the remarkable marriage that supported Dirac's lifelong productivity. Paul was famously silent, literal, and ascetic. He drank only water, avoided fiction, refused to speak French, and remained oblivious to social cues and academic politics. In contrast, Manci, sister of physicist Eugene Wigner and a Hungarian émigré, was his complete opposite, extroverted, passionate, protective, and highly social. Their union created a perfect balance. With Manci in charge of everything else in life, Dirac was free to maintain his deep focus on research, allowing their marriage to thrive for nearly 50 years. As Paul Dirac entered his later years, his relentless pursuit of mathematical elegance led to the development of three foundational concepts that would greatly influence future generations of theoretical physics. First, in 1931, he proposed the idea of magnetic monopoles, hypothetical isolated north or south magnetic poles. This concept provided a brilliant mathematical explanation for the quantization of electric charge throughout the universe. Next, his 1937 large numbers hypothesis advanced a bold cosmological speculation. Fundamental constants, such as the gravitational constant, are not fixed but gradually weaken as the universe ages. Finally, in 1962, Dirac introduced the Dirac membrane model, which investigated vibrating extended structures. Although it was originally intended to model the electron, this concept ironically became a direct mathematical precursor to modern superstring theory and M-theory. After holding Newton's prestigious Lucasian chair at Cambridge for 37 years, Paul Dirac retired in 1969, marking the beginning of the final chapter of his life, the transition to Florida. In 1971, he was successfully recruited by Florida State University and relocated to Tallahassee, where he adopted a quiet and rigorously ascetic lifestyle. True to his simple nature, Dirac found peace in regular physical activity, taking long, strenuous walks in the woods and chopping his own wood. Always allergic to pretense, he routinely declined honorary degrees, knighthoods, and media attention. The only distinction he accepted was the Order of Merit, a rare honor that allowed him to happily avoid titles, preferring to be known simply as Mr. Dirac. We conclude our journey on October 14, 1984, in Tallahassee, Florida, marking the final resting place of a true titan. Paul Dirac's headstone, simple yet profound, bears his name alongside his greatest mathematical legacy, the Dirac Equation. His passing prompted a global outpouring of grief from the scientific community. To honor his monumental contributions, a commemorative stone was unveiled in Westminster Abbey in 1995, appropriately placed near the final resting place of Sir Isaac Newton. Although this man of few words has passed on, his elegant equations will forever resonate with the cosmos, securing his immortal legacy as one of humankind's greatest scientific minds.